Okay, so this is lesson 2.1 on rates of change and limits, right? So we are going to go ahead and start looking at limits and how it pertains to our functions, and really how we can look at it in terms of the functions being continuous or not. So, limits is just another way of saying y value. So it's really asking you to look at the function and say, what is this y value as x is approaching this x value? So most of the time it's not too hard to see, because even if there were a little empty space there, if you step back far enough away from this function, you will not be able to see that little break. So we're really trying to say, hey, squint your eyes, go really, really far back. What is this y value supposed to be that will close up this graph? So for example, you've seen graphs that look something like this, where it goes, oops, sorry, that is really big, where it goes something like you have a line and then the hole and then the line right there, right? We put that hole in there, but when you're really graphing this out, it looks something like this when you zoom in. But when you zoom far out enough, right, far out enough, like so, like even I can't see the hole at all if it's that far away. So that's what we're trying to say, that if you really can't see the hole, what would that value be, right? So that's what limit really is. So because limit is a y value, it's a number. So we're trying to remind you that, hey, because it's a number, you can do a lot of things with just numbers. You can add them. So here's your sum rule. You can add, you can subtract, you can multiply, right? You can even divide if one of your limits is not 0. You can also multiply your limit by a constant, a number on the outside. So you can kind of take that number outside and say, hey, 2 times this limit, right? 2 times this function. So take that 2 outside. And even if you want, you can even take it to a power. So limit can be taken to a power of a number to a power, something that we can actually do, right? So a lot of the normal order of operations that we can do with a number, we can do with limits, because limit, again, is just a value. It's a numerical value. So we can do all these operations with it. Okay. All right, so let's go ahead and quick review this. So there's a lot of blobs here. Yes, I know, because I don't want you to see the work yet, right? So first of all, it says determine the limit by substitution, support by checking your graph. So we're going to go ahead and plug this in, right? That's what you really do. First thing you do with limits is you plug it in and see if you get an answer. So we're very lucky. We plug this in, we get a beautiful answer, right? Because there's not a number that gives you a 0 in the denominator. So it gives you this nice 5 here. So you plug in the 2, you get a 5. Okay, nice and easy. Now, how do I graph this function? Now, remember, this is a rational function. What you really want to remind yourself to do is really to remember to watch out for asymptotes, watch out for things that can reduce out. So make sure the first thing you want to do is you want to factor. Factor the top so that it's x plus 2 times x plus 3, and then you have your x plus 2. Notice these 2 reduces out to be 1, so you're really graphing the graph of x plus 3. But what about this 1 that you reduced out? It's not gone. It thus creates a removable discontinuity. It thus creates a hole in your graph. So where is that hole? Where does it reside? Well, first thing you want to do is take this x plus 2. So they go to 0. So you get x equals -2. And then plug that back into your function to get 1. So y equals 1. So your hole is a -2 comma 1. And so when you graph this out, you'll see something like this, where this is the original line of x plus 3, right? This is x plus 3 going through the y-intercept, and then your slope of up and right 1, up and right 1. But then you have this awesome hole here that we said is going to be a -2, 1. So that is where your removable discontinuity will be. So that's how you graph this function. Okay. All right. Next one, you have 1 over, when you plug it in, you get 1 over 0 squared. Well, remember, you can't really divide by 0, so what would that do to my limit? What would that look like, right? So it's undefined, right? So the limit technically does not exist, and this is where some books are a little bit different. In my opinion, this one actually is infinity. And how do we know that? We will plug in some values into t-tables and try this out. So this one, when you have a limit like this where you plug it in, it doesn't give you a nice value, it gives you something undefined. You always want to double check then to see if you can do some algebra to clean it up. Well, no algebra here, nothing to clean up. So then what's your step 3? Step 3 would be then to look at the graph and see if you can look at the, identify the limit from the graph. Well, this one, when you plug it into the t-table, I plug in my usual -2, -1, 0, 1, 2. So I plug in -2, I get 1/4. I plug in -1, I get 1. 0 is undefined. and I plug in 1, I get 1/4. So when I graph this out, I would notice that it looks kind of like a volcano. It's coming up from both sides, coming from both left side and right side of the x-axis. You're going up towards infinity. So really, some books will define and say the limit of this is infinity. So does not exist usually means that because your two limits are not matching up, but if they're going towards the same thing and they're rising at the same speed, they could essentially go towards infinity at the same time. So both are acceptable. And again, we'll talk more when the AP review comes up to see what is more accepting from the AP classroom at this point. Okay. All right, next. Oh, this is the one I was talking about. So we have now this rational function. So what happens when you plug it in? Well, when you first plug it in the 2, you're going to get 0/0, right? So what do you do when that happens? Well, then when that happens, you got to reduce. So notice how I factor the top and I factor the bottom. So I would get a nice t minus 2 here, and t minus 1, and t plus 2 on the bottom, t minus 2 on the bottom. So these two reduce out to leave you with this function right here, right? And I wanted to know where my whole would be, my removable discontinuity would be. So notice how then I go ahead and solve for this. You get t equals 2. That's why I plug in the 2 into this function. So that's how you get 2 minus 1 and 2 plus 2. So my removable discontinuity is at 2, 1/4. Okay. And this was my first try. So on the left hand side here, I told you that when we approach problems like this, we will always try to plug it in first. And I got a weird 0/0. So I can't do that because it's a weird value. So I'm going to go ahead and use algebra to factor it and see if I get a better answer. Okay. So my focus then is now to graph this function, and keep in mind I have a hole right here at 2, 1/4. Remind you of how to graph a rational function like this. The denominator is now my vertical asymptote, so t plus 2 set equal to 0. You get t equals -2 to be your vertical asymptote. Your top has a t, the bottom has a t. Your the powers are the same. So your highest polynomial function is the same. There's a single t on the top and a single t on the bottom. You reduce it out, you get y equals 1 to be your horizontal asymptote. So your graph is going to look something like this. See how my vertical asymptote is at -2, my horizontal asymptote is at 1, and keep in mind my removable discontinuity at 2, 1/4. And so that will be my graph here. Okay, so what is the limit? The limit is 1/4 because see that hole right there? If you're coming from the left and coming from the right, you will see you're going towards the same y value here. And that y value, if you were to patch it up, would be 1/4. Hence, that's the answer of my limit. And that's why I boxed it here. The limit of that function at t equals 2 is 1/4. Okay. So when we have trig functions like this, there's something you need to know. So trig functions are, some limits are very, very cool. So one that you need to know is sine of x over x. So first thing I do, of course, is what I suggest you going to plug it in. Notice again, you get a weird 0/0. So one limit that you want to spend time to memorize is limit as x approaches 0 of sine x over x. It's actually equal to 1, right? It's very weird. I know, because when you plug it in, you don't get 1. But when you graph this out, you actually see that equals 1. So how does that help? Well, I can use that to help me solve this out by breaking apart the sine of 2x function. Back in trig, you had a double angle formula, and hence that's why I'm able to write it as change the sine of 2x here into 2 sine x cosine x, right? And then I put the sine x over x right here, and I put the rest of it 2 cosine x by itself, because you can remember you can multiply your limits, so you can actually split it up from before it got multiplied together. So then that way I can see this limit approaches 1, and then this limit I can go ahead and plug in 2 times cosine of 0. Cosine of 0 is 1, so 2 times 1 gives me that second limit here, and then my final answer would be 1 times 2, which is 2. This time you should use a calculator to graph this, right? So again, we don't say this often, but using a calculator would be a good idea to kind of see what this graph looks like. If you use a graphing calculator, you will see that your graph looks something like this, with a nice little hole right here at 2, right? So at limit as x approaches 0, the value is 2. It's an open circle here, and this oscillates. It goes very quickly down, and it kind of dies out and kind of approaches 0 at both ends like that, if you zoom out far enough. Okay. All right, the next picture here is just kind of remind you of all the different limits we have. So it can remind you of how to look at the limits. Remember, there's some one-sided limit, there's some two-sided limits, right? So first thing says limit approaching x as x approaches -7. And this negative up here, that's telling you we're coming from the left side, from the negative side. Not going to the negative, but coming from the negative. So where's -7 on my graph here? -7 is right here. So as I'm coming from the left side, where's my graph going? It looks like it's going up to infinity. And hence, that is my answer for the first limit. Okay, now let's come at it from the other side, from the positive side. So coming from the positive side, where's my graph going? It's going down, down, down to -infinity, hence that is my answer. So, does the limit exist at -7? Well, one side of it is going up to positive infinity, one side is going down to -infinity. They're never going to meet up with each other, so the limit does not exist. So, a lot of times people shorthand it with D and E, and that is totally fine. Now, does the value of -7 exist on this graph here? Well, if you were to graph this out, right, you know that there's an asymptote here. So that means then the value doesn't exist at all. So the value will be undefined. So please make a note, mental or literal, that limits you say does not exist. Value you say undefined. Don't mix those two up and don't confuse those two. You never said that the value does not exist, and you never say that the limit is undefined, right? It doesn't exist because there's no limit for it. Okay. So next, we are looking at limit as x approaches -5 from the left side. So -5 is right here. We're coming now from the left side. Okay, so coming from the left side towards it. Oh, it's ending up at 1 here, right? That y value is 1. Doesn't matter if it's open or closed. It looks like it's stopping at 1. That is my limit. The answer is 1. Coming from the right side, coming from the positive side, my graph ends right here. Again, it's open. I don't care, but it ends at 2. Hence, that limit is equal to 2. Okay, now I'm looking at limit as x approaches -1 from the left side. So -1 is right here. That's -1. Coming from the left side here, oh, I'm ending right here at +4. Beautiful. Coming from the right-hand side, coming from the positive side here, I'm also ending at 4. So yes, that works. They are coming towards the same number. Because they come towards the same number, the limit as x approaches -1 from both sides, from left and right side, is equal to 4, because they match up. Okay? More importantly, does the value exist there? Yes, it is a closed circle, so the value is also 4 at that point. So that is when my function is continuous. Even though it looks like a weird angle there, it is continuous because the limit does exist on both sides. They equal the same number, and my value is defined at that point. So that thus sets the rule for continuity. So the function is continuous at that point. Okay. All right, now let's look at the positive side of my graph. I have +4 right here. If I approach +4 from the left side, from the negative side, my graph ends right here. I know there's a dot there. No, I don't care. I end right here. My graph stopped right there. So my value is, +4. If I'm coming towards +4 from the positive side, from the right side, my graph ended right here at -2. So the limit as x approaches 4 from the right side is going to be -2. Once again, because these two limits, one's up here, one's down here, they're never going to meet each other. So the limit as x approaches 4 does not exist again because there is nothing there, right? But the value of 4, is the value of 4 defined? Yes, that's where this closed circle is. That's the value of 4. The value of 4 is defined at +2. Okay, all right. A few more here. Just kind of remind you of all the weird things here. Limit as x approaches 8 from the negative side. So here is 8. That's the value of 8. I'm coming towards it from the left side, and I see that it is touching the x-axis. So the answer is 0. So the limit is 0. Okay. Coming from the positive side, where did I end up here? I end up at +3. So that's where my limit is. Again, please don't get caught up on the open or closed circle. It really doesn't matter in limits. Okay. All right. Limit as x approaches 11 from the left side. So 11 is right here. Coming towards it from the left side, I have defined my limit to be -3. Okay. If I were to ask you limit as x approaches 11 from the right hand side, notice how there's nothing here. You would just go ahead and say it does not exist. Don't make it anything. The last example here is just to remind you that limits don't have to be on the endpoints of my graph. I could be somewhere in the middle. So x approaches 9. So here's 9. What is this value here? What is this limit? Well, both sides are approaching the same number, and that value, that y value, is 1. So that is the limit as x approaches 9 is 1. Okay? All right, that's it.